Hello again. This week's discussion on the concept of deadlocks and inter-process communication. Our goals include gaining an understanding of deadlock, starvation, and priority injection. We also investigate several ways for preventing, avoiding, and detecting deadlocks in computer systems. And lastly, we will dive into the domain of inter-process communication. We will explore communication methods like shared memory and message passing, with a particular emphasis on their use in client-server systems. So remember that in previous lectures, we explored a range of synchronization tools like mutex locks or semaphores. They are important system resources, but they also often contribute to deadlock situations. For example, one lock may protect access to a queue, while another secures access to a linked list. To avoid conflicts on data structures, each lock is assigned its resource class, so some procedure is required at this point. You surely remember that a process must request a resource before use and release it afterward. Additionally, processes have the flexibility to request multiple resources for their task, but this request, you should note that, so their request must align with the total available resources in the system. Simply, a process cannot access 3 printers if the system only supports 2. So let's remember the procedure in utilizing a resource. So in the standard mode of operation, a process follows this when utilizing a resource. Okay, so initially the process makes a request for the resource. If the resource is currently unavailable, perhaps due to being used by another process, so the requesting process enters a waiting state until the resource becomes available again. So once the process successfully acquires the resource, it is permitted to operate on it. For instance, if the resource is a printer, the process can proceed with printing a document. Or if the resource is a specific file, the process can write something on it. So it can perform the intended operation associated with that resource, okay? After completing the required operations, the process must release the resource. With that way, it makes the resource available again for other processes. Actually, this step is crucial because it ensures efficient resource management, as it allows other processes to utilize and the release resource and prevents unnecessary contention. To sum up, a process's normal operation flow when interacting with a resource is request, use, and then release the resource, okay? So by following a coordinated sequence, unnecessary competition between processes is eliminated. Undesired competition or race conditions are eliminated. However, when it comes to developing multi-threaded applications, developers must be aware of the possibility of deadlocks. These locking mechanisms serve as guardians against race conditions. However, developers need to design carefully and also pay close attention to the acquisition and release of locks. I can say that any failure can result in deadlocks, as it illustrated in the dining philosopher's problem that we saw last week. So a deadlock in an operating system basically occurs when 2 or more processes are unable to proceed because each is waiting for the other to release a resource. In other words, deadlock occurs when 2 or more processes are waiting indefinitely for an event that can only be caused by only one of the waiting processes. So let's consider a simple example involving 4 roads, A, B, C, and D, and intersecting at a point. Cars from each road want to cross the intersection, but there must be traffic signals controlling the traffic flow. However, due to some issue in the traffic signal system, I don't know, maybe because of malfunction or mismanagement, cars are unable to move because each road is waiting for another road to be clear. So cars from each road are stuck, creating a deadlock. Okay. So road A might be waiting for B, road B waiting for C, C for D, and D for A, and resulting in a circular dependency where no car can move. So car ends up deadlocked at the intersection. To resolve it, of course, the traffic signal system needs correction. Cars may need to be granted the right of way in a coordinated manner to break the circular dependency and allow traffic to flow smoothly. Let's consider another scenario. In this scenario, it involves a hostage situation with a cop and a criminal. So criminal has taken a hostage and a police officer has taken the criminal's friend. The criminal demands the release of their friend, threatening not to release the hostage unless the cop complies. And this is also for cop. This situation creates a deadlock scenario where both parties aren't willing to meet the other's demand. The cop is holding the criminal's friend and the criminal is holding the hostage. In the solution of this, it might involve a third-party mediator, a change in demands, or a coordinated effort to ensure the safety of both the hostage and criminal's friends. So these two cases are similar to this implementation. So consider two semaphores, S and Q, okay? And both initialize to 1. The processes P0 and P1 are executing these following codes. So in this implementation, actually P0 is waiting for Q, and Q is held by P1, and P2 is waiting for resource S, and S held by P0. So that we can say that deadlock can arise if the following 4 conditions hold simultaneously. Okay. So let's see these conditions. Two or more resources are non-shareable. Only one process can use at a time. This condition, namely mutual exclusion condition, or a process is holding at least one resource and waiting for another resource. This condition is named as hold and wait. A resource cannot be taken from a process unless the process releases the resource. This condition is named as no preemption. And the last one, a set of processes waiting for each other in a circular form. So this is circular wait. So we can say that deadlock can arise if the following conditions hold simultaneously. I also want to define two concepts before moving on deadlock avoidance and detection part. Firstly, starvation is a situation where a process may be indefinitely blocked. This occurs when a process is waiting for a resource and is never removed from the semaphore queue, especially in scenarios where last in, first out queuing is employed. Secondly, priority inversion is a scheduling problem that arises when a lower priority process holds a lock needed by a higher priority process. In such cases, the higher priority one is delayed as it cannot proceed until the lower priority process releases the required lock.